Okay. Hello, check. Okay, it's working.
Yeah. Okay. Sounds okay.
We'll say, okay, good morning, everyone. So let's get started with the one more event and a small scale event that we are organizing and promoting here at the IIP. And I just like to remind you that we had this year already a mini course on collider physics, and we had one on gravitational waves, and we had one on phase transitions, and now you're having the fourth on dark matter neutrino physics and baryon asymmetry. So that's the fourth small scale event that we are promoting this year. We have more to come, about four more to come throughout the year. Okay? So it's my pleasure to introduce you to Debasish. So he's a world expert on dark matter. So I've known him from papers from a very long time. So we exchanged emails several times about papers and because we work on similar topics. And it's quite a pleasure to have him here for 3 weeks. And I'm pretty sure that you're going to have a very, very pleasant mini course. And I'm really glad that you came here all the way from India to share your knowledge to the students and everybody who is in the audience. Okay, thank you so much.
Okay, thank you. All right, so I'll start. Um, okay, so thank you very much for the invitation and the introduction. So today I'll talk about neutrino physics, as you already know. I'm not sure if the size of the letter is okay. All right. So so since the time is very constrained, so I have tried to make a balance between the pedagogical and as well as informative. But I'll be happy to answer if you have any questions at the end about some of the details which I may not be able to cover as much as much as I would have liked to. So let's start with how neutrino came into the picture. So we know that Pauli proposed the existence of the neutrinos because of the problem in beta decay. So what happens in beta decay, for example, I know that if you have a nucleus, it goes to something else which has one more proton. This is atomic number plus electron. So the electron is usually called the beta particle. So if you look at if you count the number of beta particles or electrons and plot it as a function of their kinetic energy, it's a charged particle, so it's easy to find the kinetic energy of a charged particle, unlike neutrino. So what you expect if it's a two-body decay, this guy is at rest, so the momentum, so these two guys should be going equal and opposite. So you should expect that all the electrons should fall on this line. They should have just one energy, one kinetic energy, which is equal to the mass difference between this guy and this guy. Okay, but what people observe is that they found a continuous distribution where the tail actually meets the endpoint of the kinetic energy spectrum. So from that actually does not agree with a two-body decay. So then Pauli proposed that it has to be a three-body decay at least, and he added something like a neutrino. Okay, so there's a difference between neutrino and antineutrino, which I'll talk about. But let's say this is just a particle, which is a fermion, and very light because you don't have too many mass to accommodate in the final state phase space. But it can carry lots of energy, okay? And that actually tells you that you are getting some of the electrons with less energy than you would have expected if it is a two-body decay, because some of the energies are carried away by the neutrinos, okay? So if you look at the nucleon level, this is basically a neutron going into a proton plus electron plus antineutrino of the electron type. Okay, so similarly, you can take all possible permutation combination of this process. For example, I can also think of something like nu e bar plus p going to n plus electron. Okay, so I can always take one particle from this side to this side and just flip the quantum numbers. Okay, that's what we can do. You can also have something like, say, reverse of this process. And that's how actually neutrinos are detected in different experiments. For example, if you read about, I'm sure you already know, if you read about how the antineutrino was discovered by Rines and Cohen in their experiments. So what they do is that they put a water tank, huge water tank, and they find that they put it in front of a nuclear reactor from where you have lots of antineutrinos of electron type. It will come and hit your water, which is basically proton, and it will convert into a neutron and electron. Okay, sorry, neutron plus positron, right? Because the proton is a charged particle. Okay, so what happens is that this positron will actually annihilate with an electron, which is already there in the detector, and put a gamma rays. Okay, and that gamma ray you detect, and then that is a clear signature that this process has happened in that experiment. Okay, but if you want to do the same thing to detect neutrinos, not antineutrinos, it's not going to work, because if you do it like this plus proton, you cannot produce neutron and electron, for example. Okay, or you cannot produce neutron plus E plus. This is because of the lepton number. Okay, which which I'm sure you know already. I'll talk about it later on if needed. So this has lepton number +1, and this is -1. So the lepton number is not conserved. So you cannot have this process. Okay, but you can detect solar neutrinos, because from the sun you have lots of neutrinos coming. So you can detect this by the neutron plus neutrino, and it's going to proton plus electron. Okay, so this is how Ray Davis detected solar neutrinos. What he did is he had a huge chlorine tank. So chlorine, so neutrinos will come and hit one of the neutrons inside chlorine and actually convert it to argon. So he counted the number of argon atoms which is produced in the huge chlorine tank, and that could give an estimate about the neutrinos coming from the sun. Okay, so all these things one can understand by just looking at the standard model Lagrangian, which tells you how these neutrinos actually interact. Okay, so we started with the Fermi theory first, and Fermi theory is a non-renormalizable theory. So then we moved to the renormalizable version of this theory of the electroweak interactions, and that Lagrangian can actually explain the rates of all these processes which we have observed over last few decades. Okay, so let me write down the Lagrangian. So in the standard model, I know that the Lagrangian, which is important for the neutrinos, is, so first of all, you have the kinetic term, then you have the charge current in the familiar form, and the neutral current. Okay, so this G is the SU2 coupling, and your cos theta W, so tan theta W is G prime by G, which is the U1Y. Okay, so this actually explains both charge current as well as neutral current. Okay, so all the processes that I mentioned, these are basically charge current dominated processes. Okay, so if you want to say it's a neutral current processes, then the initial state and the final state will be same. Okay, so now we have observed that neutrinos have mass. I will actually talk about it, how do we know that neutrinos have mass. Now, if you want to have neutrinos massive in the standard model, it's not possible unless you introduce a right-handed nu r. Okay, so in the standard model, we know that all the neutrinos that come is basically part of this lepton doublet, which we write as nu L, EL. Okay. On the other hand, if you look at the way we write down mass terms, right, mass terms would be like of this form. So this is the mass term, which gives you the mass of the electrons, because after the Higgs gets a FeV. Similarly, if you want to do for the neutrinos, you want to introduce a nu R, which will couple to the L and H to give you the neutrino mass. Okay, so if I write that term by using a hypothetical particle called nu R, So that will give me the mass of the neutrinos. It's a Dirac mass, of course. There are certain aspects of writing this term and not writing something else, which I will talk about as we go on. But the essential idea is that once we write this term, the phenomenology for the lepton sector is exactly same as the quark sector, because you have two different masses, one for the up type leptons, one for the down type leptons. So you can do all this diagonalization of the mass matrices for the up type and down type. And these are Dirac mass matrices, so they are not necessarily Hermitian or symmetric, or they may not have any symmetric type of features. So you need a bi-unitary transformation. So you need basically two different unitary matrices to diagonalize arbitrary complex mass matrix of up type and down type leptons. Okay, so if you do that, you can write down y nu, which is this one, diagonal. So you need two. You can write it like this. And similarly for the YL or YE, you can have UL, YL, diagonal, and KL, dagger. Okay. So if you do that, you want also realize that all these matrices you will not be able to see in physical processes. Only a combination of them you will be able to see. Basically, because your charge current interaction couples only left-handed fermions, so you will be basically able to see a combination of this UL and U nu, just like the way you saw this in the CKM. So you can do the same thing for the CKM, but the ones appearing on this side, this K, is basically you can rotate the right-handed guys and the left-handed guys, because mass matrices contain both left and right. But ultimately, what is important is the rotation that you use for the left-handed guys only, because that is only coming here. Right-handed guys will not come. Right-handed guys will come in the neutral current interaction, but that's diagonal. Okay, so all matrices will actually disappear there. Okay, so here, if I do that, so now I can go to the mass basis, because these are flavor basis. So I can go. So this is flavor basis. I can go from this to U nu. This is a mass basis. I will denote by I, and this is a Greek, and this is Latin. And similarly, I can do for the nu alpha R, K nu, nu I R. This is anyway not going to be important for the charge current. So same thing I can do for the L, L, and LR as well. And eventually, if I now in this Lagrangian, I will go to the mass basis. So if I go to the mass basis, the same like the CKM will come, which we'll not call CKM because this is a lepton sector. We'll call it PMNS, okay, or lepton mixing matrix. So I can write it down. If I go to the mass basis, I will write it as G by root 2 mu plus. I will write, so here it is flavor. If I want to explicitly write as flavor, so I will go from the flavor to the mass basis. So I will now use this I symbol, gamma mu, and I will rotate this guy with U nu. I will rotate the lepton, charged lepton, with UL, okay? Since one is bar and one is not bar, so you'll get a one UL dagger, U nu, okay? So I will get a combination of U nu dagger, UL, IJ, EJL plus addition conjugate, okay? And this is basically I know as the lepton mixing matrix, analogous to CKM, okay? And it's a 3x3, so I also know how many angles it should have. So it should have 3 angles. And it should have one physical phase, CP phase. Okay, so the number of physical phase you always count as n minus 1, n minus 2 divided by 2. Okay, usually it can have 6 phases, but you can rotate because you have 6 leptons. Out of them, you can rotate at most 5. So it will help you to get rid of 5 phases. Okay, so 6 minus 1, 6 minus 5 will give you 1. Okay, so if you put n equal to 3, it will give you 1 CP violating phase. Okay, so we assuming that neutrinos have mass, we can do all these things, and we can relate the flavor state as the mass states. Okay, and now let's see what is the consequence of that. Okay. All right. I can use this? Okay, perfect. Okay, so now, all three, okay, great. So now I can write, since I have already done this a transformation from the flavor to the physical basis, so I can write my flavor state as a coherent superposition of the mass states, okay? And this I will write the mixing matrix, okay? So if I can always choose one of the mixing matrices to be diagonal. That's always an option, because only the combination of them, U, nu, dagger, U, L, is going to be important in your experiments, okay, or in your interaction. So I can take UL to be diagonal, so this matrix will be just U nu. I can always make that choice of basis, okay. So now if I do that, so now I can find out, because this is a mass eigenset, this is the eigenset of the Hamiltonian, so I can find out if this is there at t equal to 0, at x equal to 0, what will be the state after some time and after it propagates some distance x. Okay, so this is just the unitary evolution in quantum mechanics, which we know very well. So I can write down nu alpha t x as u alpha j e to the power minus I p dot x. So that will be I e. So this is I. So this is j. So this should be j. So e j t plus I p j x nu j. Okay. So this I can write at t equal to 0, x equal to 0 also, to be precise. So that's how we know that this wave functions, or this cats, actually evolve with the time. Okay. Now, if we want to find out that, okay, I create alpha type of neutrino flavor at t equal to 0, x equal to 0, what is the probability that it will actually transform into a beta type after traveling a distance of t and x, distance of x in time t? Okay, so that is just you have to take the bracket and find out the amplitude. So that is basically nu beta, nu alpha, tx. This is what we have to calculate. This is the amplitude of the probability that this alpha will be detected after traveling a distance x in time t as a beta. Alpha, beta are different, of course, as of now. You can think of it as electron type neutrino and a muon type neutrino. Okay, so this is very simple, like a quantum mechanics. So I can write this as J. So I have to write, so I can similarly write this guy as a linear superposition of the mass eigenstate, but take the complex conjugate, because I go from cat to bra. So I can, so that's why this beta will not have any conjugate here. So this will be k e to the power minus I e j t plus I p j x. Okay. So nu k, nu j, these are orthonormal states of the Hamiltonian. So I can use all those orthonormalities. So that will actually force me to have k is same as j. So I can simplify it. Alpha j star beta j to the minus I e j t plus I p j x. Okay. Now this is the amplitude. So I can find out the probability by taking the mod square of the amplitude. Okay. So the probability will be probability that it will go from alpha to beta is p alpha beta mod of this guy whole square. Okay, so I do it. So I just multiply it twice. I just have to keep track of the indices properly. These are dummy indices. If we have more dummy indices, we use different notations so that I don't confuse between different dummy indices, because they have to be summed over separately. So this will become beta j. So I'll choose now alpha k u dagger beta k e to the power minus I ej minus ek t plus I pj minus pk x. Okay. So this is the probability. So now I can I can average over the time because I'm not sure, like if I'm looking at a beam of neutrinos coming from some distance to here, I am not exactly counting like at what time this guy is coming, what time is this guy. So I'm actually averaging over. I'm counting the number of events at my detector over a period of time. So I'm not really bothering about what time they are actually coming. I'm just interested in what flavor, what number of neutrinos I started at that point, what number of that particular flavor I'm counting at this point. Okay, so that's why I can average over the time. So average over time. So P alpha beta usually a function of x and t, but now I will write it as a function of x only by doing an average over time. X. Okay. So and I'm just keeping it a normalization constant. That means if I get something here, I will actually cancel it with the n, such that I know that the unitarity tell me that total sum of probability cannot be more than 1. It has to be equal to 1. So it's just a normalization. And now I can normalize it and find out the expression for the probability. And I can note down an identity for the Dirac delta function, which is dk by 2 pi e to the power minus I kx. Okay, so if I use this identity, I will get a Dirac delta function in terms of the energies because I'm integrating over time. Okay, so I'll get 2 pi delta function ej minus ek. So I will write it as 1 by n u alpha j star u beta j u alpha k u beta k e to the power I pj minus pk x and then 2 pi delta function ej minus ek. So what it will actually force me to have same value of ej and ek. Okay, so I can, if I make sure that ej and ek are same, I can actually get rid of this delta function. Okay, that's what it means, right? So all I have to worry about is this guy. Okay, what is this pj minus pk? So I can use the energy momentum expression. So I can write I pj minus pk x. So this I can write as I e square minus mj square minus e square minus pk square. Oh, sorry, mk square. mk square, right? So I'm already assuming that e's are same, so I don't have to really worry about the difference in e. So if I take mass to be small compared to E, which is always true for neutrinos because, as I will tell, neutrinos have very tiny masses, but most of the time it goes with a very high energy, relativistic always. So this is always true for relativistic neutrinos. So if I do this, I can actually Taylor expand it, and I will find that ultimately your P alpha beta will come out to be U alpha j star U beta j U alpha k U dagger beta k e to the power minus I mj square minus mk square divided by 2e x. Okay, so this is my expression for the probability. Okay, I can also simplify it, so I don't have to worry about it. So I actually make sure that this n and 2 pi actually cancel out, so that this is actually consistent with the total sum of probability equal to 1 because u is a unitary matrix, right? So U is a unitary matrix. So in two flavor, it's very simple. Two flavor, that means you assume that only electron type neutrino and muon type neutrinos are there. There's no tau. So then this guy, you know that in two flavor, there's no CP phase, and it's a two-dimensional plane, so there's only one angle. Okay, so it's very simple. So I can write down U as just cos theta, sine theta, minus sine theta, cos theta. If you replace it here, you will get the expression for the probability for alpha beta as a function of x. Okay, I will skip some steps because otherwise I will run out of time. It's a very simple algebraic computation, and use this form here everywhere. Sum over j and k. Keep alpha beta intact because alpha beta is coming here. You can sum over j and k, and this will come out to be sine square 2 theta 1 minus sorry, I can directly write the final expression. Sine square 2 theta sine square delta m square x divided by 4e. So this delta m square is m2 square minus m1 square. Okay, because there are two flavors, so only 1 and 2. Okay, so this actually tells us two things, two very important things, that neutrinos will go from one flavor to another flavor, and it will depend upon two things. First thing is that it should have mass, not only mass, but it should have a mass splitting between the two types of eigenstates. So that's very important. If it is massive but delta m square is 0, that's not going to matter. It also should have some mixing, okay, and that is coming from here. Okay, so that means this U leptonic mixing matrix I talked about, it cannot be a diagonal matrix. Okay, it should have some off diagonal entries. Okay? So that's why both of these things will come into the picture. And in general, so this is the oscillation probability for beta to alpha. You can also find out what is p alpha. When you start with alpha, what is the probability that you will get alpha here? Okay, so it will be just 1 minus of this. So in general, you can write it as p alpha beta minus of this quantity. Okay, so if alpha is not equal to beta, then this will come drop out and you will have only this term. Okay, so in 3 flavor, it will become a bit more complicated because your U have 3 angles and 1 CP phase, which will come into the picture. So I'll not do these things, but so the CP violation you will not be able to see here because there is no CP phase. But if you go to 3 flavor, you can see the CP phase, and people have actually observed. So how do you see that there is a CP phase in Neutrino oscillation? For example, you calculate P beta going to alpha. You also calculate P beta bar going to alpha bar. You start with an anti-neutrino of electron type and see whether you get a muon type anti-neutrino here. You start with an electron type neutrino there, find out whether you get a muon type neutrino here, that is here. If this two term is not equal, it shows that there is non-zero CP violation phase in the leptonic mixing matrix. Okay, so this is actually people have already seen, and that actually indicates that there is CP violation in the lepton sector. We have not measured it with full confidence, but there is a indication that lepton sector CP violation is there, and it could probably be stronger or larger compared to the quark sector CP violation, which is very small. All right, so now this is what we have discussed so far is the oscillation in vacuum. Okay, I have not assumed any matter. Okay, so now if we assume any matter, the things will slightly change. Let me start here. What will happen? Let's start with the Fermi interactions, which I know very well, because I'm interested in low energy oscillations. So I really don't have to worry about that renormalizable standard model. I can start with effective theory because I'm interested in low energy. So this is GF by √2. So the Fermi interaction is one minus gamma 5 E. Okay, and this GF is just 1 by mw square, g square by mw square, up to a factor of 4√2. And this I can actually rewrite as GF by √2 E bar gamma mu 1 minus gamma 5 E mu E bar gamma mu 1 minus gamma 5 mu E. So how can I do that? I can use the something called Fier's rearrangement. I can use this identity, which we know in QFT. This is equal to, I can actually combine the electron with the electron and take the neutrino here. Okay, so that I can do, but I'll get a minus sign. That actually removes the minus sign which I started with. Okay, so I can write this as EL bar okay. So this actually, this is very convenient because what we're looking at the neutrino oscillation probability. And if this is the interaction, if neutrinos are traveling through matter, it will see because matter has electrons and protons, so it will see electrons. And the thing is that if we have electron type neutrino, it will see electron. If we have muon type neutrino, it will see muons. That's how we write the interactions. But the problem is that matter doesn't have muons. Okay, so only electron type neutrino will see the presence of matter if it is traveling through a medium, not free space. On the other hand, if we have only muon type or tau type, they are not going to see anything. Okay, they will almost go like a vacuum. Okay, so one has to take this into account. So once again, I can average over this term, which is expectation value of this quantity, that will tell you what potential electron type neutrinos see when it actually travels through matter which contains electrons. Okay, so I can take an expectation value of this quantity. I can write down these electrons in terms of the fields, in terms of this a dagger, a, b dagger, u and v e to the power minus I p dot x plus p dot x, and I can actually write it in a simple form. So let me do that. So e bar gamma mu 1 minus gamma 5 e, so that I can write by writing this e as Fourier series in terms of the creation and annihilation operators. So I can write this thing as sum over spin dqp fp these are the brackets gamma 5 e and e p s. Okay, let's keep it separate. And this I know, this is just you act the field on the vacuum and you get this state. Okay, that is the idea. And this, if I write down the Fourier space, so for example, this guy E, so this is the electron, not positron. So this is E P S is basically you act on the vacuum, this A P S dagger. Okay. So this A comes with the U's and U bars, and the B comes with the V and V bars. So since this is electron, I will get only U and U bar if I do this average. Okay, this half factor is for the spin, and this sum over spin. Okay, so this will give me, if I further simplify it, so I will get this U and U bar from this calculations, because this I will have U and U bar from this E and this E. So I will get half. I should have this. I'll have U and U bar or 5. So this I should write that this is P and S, P and S. And this will give me, so if I sum over spin, it will give me the trace. So trace of U, U bar, I know that this is P slash plus M. So this will give me half. This I can drop. So dqp. Sorry, I forgot to write this 2EP, which is always there when I write down this fields in terms of this Fourier space of A and B dagger. So I should write this 2EP. So 2EP. Then this will be FP, and then trace of P slash plus ME gamma mu 1 minus gamma 5. Okay, so if I do these calculations, I can use the trace properties of the gamma mu. So if we have one gamma mu, it is 0. If we have gamma mu gamma 5, trace is 0. So only term that is going to contribute is P slash gamma mu, because P slash already has one gamma. So this will give me so this, if I combine, this will give me trace of P slash gamma mu, which is 4 P nu eta mu. Okay, so this will give me, so this will take it to P mu, and you can clearly see that this will give you half dqp 2ep fp, and this is going to give you 4 p mu. Okay, and since we are interested in the so this is going to give you p mu, so this is going to give you energy for the mu equal to 0. is going to give you energy. So because the matter is at rest, so I'm not talking about the electrons which are moving, matter is at rest, so the free momentum is zero, so only the energy is important. So this energy will actually cancel out with this. Okay, so this 4 and this will actually cancel out, and so ultimately I will have let me go up. So ultimately I will have this quantity as 2, 2, 4. 4 will cancel out. So ultimately EP will cancel out. And I use the definition that dQp Fp is basically the number density. Okay, this is the statistical mechanics. I know this definition, so I can just write this thing as just Ne. Okay, so then my final term, which I had from the Lagrangian, if I take the expectation value of the first term, E bar gamma mu1 minus gamma 5E, I will get the effective Hamiltonian, which is GF by root 2. The expectation value I will just write as NE, and then I will have nu E bar gamma 0, 1 minus gamma 5 nu E. Okay, I put gamma 0, but because I took the gamma 0 part of here only, right? Because they are summed over. So this is basically root 2 GF NE bar gamma 0 UL. Okay, I get this extra 2-factor submerged in this 1 minus gamma 5 by 2, which is gives you the left chiral part of the neutrinos. Okay, so this tells me that I have to take this. So this is the potential which the neutrinos will see, electron-type neutrinos will see when it actually travels through matter. Okay, so this, if I take into account, I have to. So this I will call as VCC. So CC actually indicates that it is coming from the charge current interaction, because that is the interaction I started with the 4 Fermi. There will be a corresponding neutral current also, but that is not going to be important for the oscillations, because neutral current is seen by both electron type neutrino and the muon type neutrino. So if you write down the mass matrix or the Hamiltonian in the E mu, you will see a charge current here, you will see a neutral current here, you will see a neutral current here also. You will not see a charge current here. Okay, so that's why VNC is coming in both the flavors, so it is not going to give you any oscillations. It's not going to matter for the oscillations as far as the oscillations is concerned. If you want to see its role in neutrino detection, of course it is going to play a role, but this is not going to matter if I talk about only the oscillation of electron-type neutrino to muon-type neutrino or vice versa. So now if I include it, I will have to rewrite my Hamiltonian. So that will give me some more terms. So if you recall, the way I used here, so I had to write down this guy now, P, the momentum. So the momentum I could write here like this, but now I have to be a bit more careful, because energy is not just the rest mass energy, P squared by M. It is actually, you will see the potential also. Okay, so I have to write this thing in more general. So if I write down the operator, momentum operator, so since it is in the presence of a potential now, so I will write it. So this is H Hamiltonian minus potential minus mass square. So usually it is E square minus M square, which I can write this as E if I want to operate it on a state. But now it is H minus V. So this, if I expand, assuming that the potential is small, I can write this as H minus M square by 2H minus V. Okay, so I can Taylor expand it just like I did Taylor expansion there, assuming mass is small compared to energy. Here also I'm assuming that the mass is small compared to the energy, and also the potential is also small. So if, in this case, so this will give me the usual thing which I already know from there, and this is going to give me some extra term, and this is going to give me this VCC. Okay, so if I write this in the component form in the 2-flavor basis, this is going to give me E, the first term, same, right? I don't distinguish between the energy of the electron-type neutrino and the, so this is the free particle part, it's the same energy. And then this guy, because I know how to write down this is the mass eigenstate, so I can go from the flavor to the mass by using that U I use there. I can, this actually, what this does is actually takes you from m nu to m nu diagonal, something like that. Okay, so I can write down this thing here also. So u m1 square by 2e, m2 square by 2e. So this is a two flavor. So all these transpose and dagger, so this dagger or conjugate is not going to matter much because there is no CP phase. Okay, I'm not writing the neutral current. I can write the neutral current here plus NC plus NC, but that is not important for the oscillation part. So I will just write it like this. So if I simplify it a bit more, I will get the full matrix, which will give me which will help me to calculate the oscillation probability of one flavor of neutrino to another in the presence of matter which contains electrons. Okay, so if I write these things in terms of the quantities as I know, this will give me, if I use the u as cos theta sin theta minus sin theta cos theta, I can write this in a more convenient form as 1 by 4e m1 square plus m2 square. I basically want to find out, I want to separate out, because some of the terms will be same for both the flavors. So what we want is that we want to separate out the constant diagonal term, which can be multiplied with identity matrix, and the term which actually distinguishes between the two flavors, okay? Because that is going to matter for my neutrino oscillations, okay? So we can do that just by a few more steps, which I'm skipping. So I can write it as this. So this is a constant term. So this is a 2 cross 2 identity matrix, plus the more important term, which is going to be matter for the oscillation, sine 2 theta. So I can write it like this, okay? So this you can see this is identity matrix 2 cross 2, so it is not going to matter. So if I want to write NC, VNC will also add up here, which is not going to be important for the oscillation. So what I want to worry is that now how to diagonalize it, because I diagonalize it, I get to know how the oscillation happens, because this is going to give me the mixing angle, okay, right? My effective, so here I just worried about the mass matrix only, but now I have to worry about all these things because the potential is also there. So I diagonalize it. So if I diagonalize it, so I have to diagonalize VCC by 2 minus delta by 2. So I will write this guy as simply as delta, and delta by 2 sine 2 theta, delta by 2 sine 2 theta, delta by 2 cos 2 theta minus VCC by 2. Okay. So this is what I have to diagonalize it. So if you write down the, so if you do that minus lambda, take the determinant, you will find that equation which will give you the eigenvalues. The eigenvalues of this is 1, 2 plus minus half VCC minus delta cos 2 theta whole square plus delta square sine square 2 theta. Okay. Okay, so if I find out the eigenvalues, I can also find out the eigenvectors. That will give me the matrix. So that matrix will give me a sine theta, cos theta, sine theta minus sine theta, cos theta. So I can find out the effective mixing angle, because this mixing angle is not going to be same as that mixing angle, because obviously you have different terms in the Hamiltonian now, which is going to be important for the oscillation. So if I do this, I can find out the eigenvectors, I can find out the mixing matrix, and from that I can find out the effective mixing angle. And the effective mixing angle, sine 2 theta, I'll say effective, this is delta. So this is basically this term divided by these guys. So delta sine 2 theta divided by VCC minus delta cos 2 theta whole square plus delta square sine square 2 theta. Okay, so this actually tells you one important thing, is that this mixing angle, so you don't know this VCC because you do not know what is the electron density. It can go through electron density, which is changing with space. So then you have to integrate over the space also to find out the effective oscillation probability. So here I have assumed that VCC is just a constant. There's a constant electron number density. But if it varies, then you have to. So for example, you have to find out how the oscillation happens for a solar neutrino. So it is going through the sun. So sun has varying density of matter from its core to the outer layers. Okay, so then you have to integrate over that. Okay, so that's definitely more complicated than this simple analysis. But it tells you one important thing is that if this guy, so if his CC is equal to delta cos 2 theta, so these guys are the vacuum mixing angle. So this theta is same as that theta, right? But this is the effective mixing angle in the presence of matter. Okay, so and effective mixing angle will depend upon through which neutrinos are traveling, whether it is traveling through Earth or Sun or something else, it will actually decide. But the vacuum mixing angles are the fundamental ones, and we always quote those values when we say what is the neutrino mixing. Okay, so if this is equal to this, so you see that the mixing angle is very large. So this is actually called the MSW resonance. Okay, which we have seen in the when we try to solve the solar neutrino problem, for example. Okay, and this actually tells you that if you have to have this resonance, you must have, because VCC is a positive quantity, so delta should also be positive quantity. Okay, so that means that your delta, which is delta M21 square, has to be greater than 0. So that's from this, from the solar neutrino problem, I know already that the M2 is more than M1. What is M2, M1? Because you can find out, you can say that M1, M2, M3, if I go to 3 flavor, these are 3 mass eigenstates of the neutrinos. So for the solar neutrino problem, I know that M2 is more than M1. I still do not know where M3 should fit. M3 should fit here or it should fit here. That I don't know yet. We don't know yet, okay? But this is at least know from the solar neutrino problem by looking at the MSW resonance, okay? So this is, so now if you also look at VCC, which is very, very small, then what this will become same as the sine 2 theta, right? So if VCC is very small, then what will happen? You will get theta effective, it will go to theta, which is a vacuum oscillation. Okay, so it's not going to make any difference. All right, so how much time we have? $12 minutes. Okay, yeah, fine. I have something more to cover. Okay. All right, so from the oscillation data, I know, so I need to go a bit fast. So from the oscillation data, I know the 3 angles. So these are so oscillation data. I know theta 1, 2, theta 1, 3, theta 2, 3. I know delta CP. I know delta M21 square. I know delta M31 square, but only absolute value, because I do not know whether M3 is more compared to M1. Okay, but this is I know for sure, and this is of the order of 10 to the minus 5 electron volt square, so the order 10 to the minus 3 volt square. So what we do not know some of the things. For example, this guy we do not know fully. We do not know the sign of this term. This is also we do not know. This also we do not know. We also do not know the octant of this angle, whether it is more than 45 or less than 45. Okay, so these are the 3 things which we do not know yet. And you can clearly see that if you have 3 mass eigenstates, M1, M2, M3, and experiments only tell you these 2 guys, that means one of the mass you do not know, right? So the lightest neutrino mass can be 0 also. It is consistent with the data. Okay, so how do you find the effective neutrino mass? It is absolute neutrino mass. You find out absolute neutrino mass absolute neutrino mass you cannot find out from the oscillation experiments, but you can find out from the tail of the beta decay, for example. If you look at this, as I mentioned, it ends here, okay? But if you have neutrinos which are massive, if you add mass to the neutrinos, this will not end here. This will end slightly here, right? But of course, the mass is, so this is of the order of, say, this is a nuclear physics process, so this energies can be of the order of kilo electron volt or so. But if you give a slight small mass, electron volt, and all this difference is going to be very, very small. So what people actually look at, people look at the slope of the spectrum. So dn by de. Okay, so if you look at this, you get, usually you get this for m nu 0, but you get this for m nu not equal to 0. So this is an experiment which is going on in Germany, which is called Katrin in Karlsruhe. So there they are looking at the tritium beta decay. Okay, so the tritium beta decay process, you're looking at the tail of this spectrum. Okay, because they are looking at tritium beta decay because of the energy resolution will be much better compared to taking a heavy nuclei, for example. Okay, so this is one way. Another way is the cosmology. So cosmology gives you some of the neutrino mass around 0.12. If you give more masses to the neutrinos, it actually reduces the structure formation at small scales. And so from that, by looking at this different experiment, for example, recently DAISY gave some update on the mass of neutrinos, and they've said that the mass of neutrinos should be much smaller compared to what Planck gives. So this is the Planck data. So this is very interesting as far as the cosmology is concerned. So so this is how we measure neutrino mass. I can erase it. So just to quickly tell you how to get neutrino, how to generate neutrino mass. So one example I have already given, just treat them as a Dirac fermion and introduce a right-handed neutrino. So if you have a neutrino as a Dirac fermion, just like the other guys we know very well, so you introduce this guy as y nu L bar H tilde nu R plus Hermitian conjugate. Okay, neutrinos are purely Dirac. The problem is that this is a completely SM singlet. So you are not explaining why you are not writing the bare mass term of the nu R. Okay, if you do not write this kind of term, you can write this kind of term, but you are not writing. That means you are imposing some kind of U1L or some kind of discrete symmetries to actually prevent this term. Another problem is that, not problem, but it is like more of a aesthetic regions. So this, I know this is of the order of 10 to the power 2 GeV. I know that m nu is less than 0.1 electron volts. So that tells me that this guy should be less than 10 to the power minus 10, which is very small. Okay, so this is called the fine tube. Right? So that's why people talk about seesaw models. So what do we mean by seesaw? That means they allow this term, which is allowed in the standard model. So if you allow this term, which you should write unless you impose some extra symmetries, what it will do, it will introduce a extra scale to the theory, m, which is not predicted or restricted by the symmetry of the problem. Okay, so what you do is that you say that, okay, this m is very heavy. So that actually explains this mass is of the order of the electron mass or maybe top quark mass or the bottom quark mass. But if this guy is much heavier compared to that, you get a seesaw. Okay, so one guy you make heavy, it makes you the other guy lighter. Okay, so that is basically called the type 1 seesaw. So what you do is that you write down this guy nu R, then you also write half m nu RC nu R plus Hermitian conjugate. So this is called the Majorana mass term. Which you cannot write for the charge fermions because this will not be gauge invariant, but you can do it for nu R because nu R is the singlet. You cannot write explicitly for nu L also because nu L is part of a lepton doublet. So if you write down the nu L C bar nu L, that means that you are effectively writing a term L C bar L. L contains electron also, so it will actually violate the charge conservation. Okay, so you cannot write those kind of terms. And if you write this term, and you will find that you can write the final Lagrangian as minus half psi c bar m psi plus Hermitian conjugate. So this psi is basically nu L, nu R C, and this M is 0, MD, MD, MR. Okay, and this is 0 because you are not writing nu L C bar nu L. In the standard model plus nu R, simplest type 1 seesaw model, you cannot write this term. Okay, because this is coming from LC bar L. So this has hypercharge 2. Okay, you can do it by if you introduce some other field, which is called type 2 seesaw. Okay, it's a triplet, SU2 triplet with hypercharge 2. Okay, so that will allow this term. So we are not writing that. So if it is the simplest type 1 seesaw, you can write this term. And the interesting thing about this model, which I personally like this model very much because it's very simple and it's always like all the fermions have a right chiral part anyway in the standard model. So why not neutrinos? So you introduce them, but you are also forced to introduce this mass because it's allowed by the symmetry. And this explains the neutrino mass very well, because if you actually diagonalize it, you will find that the neutrino mass will go as md square by mr, if you assume that md is much, much small compared to mr. So this tells you that even if md is, say, 10 to the power 2, md is 10 to the power 2, you can still get m nu 0.1 if you say mr is of the order of 10 to the power 14. It's perfectly fine. Okay. Only problem is that this goes out of reach of all our experiments because it's very high scale. If you want to lower it down, you have to lower this also. So again, the problem of fine tuning comes. Okay. And you can also find from here that this nu L, or this heavy light, they have a mixing, which you can write as tan theta of the order of md by mr. Because in the experiment, you are going to produce only light neutrinos, okay? But if light neutrinos have a mixing with the heavy neutrinos, you can think of producing something like this. For example, if you have pp collision, and it has, say, WL, right? And it can produce a heavy guy because this will be then mixing suppressed, theta square, and this will produce lepton, E minus, and this guy can decay. So this guy can decay again. If it is heavy enough, it can also decay into E minus, and again a W, and this guy can go to JJ. So this is a very interesting signature you can find in the colliders, and this is actually same sign dilepton, which actually tells you that there is some kind of lepton number violation. What is the lepton number violation? It is actually contained in this term. Because when you allow this term, you automatically mean that this has lepton number, this guy has same lepton number as this guy, because this is bar, nu r, so the lepton number cancels out. All the terms that you write in the standard model, they obey lepton number conservation. But once you write this term, whatever u1 charge you assign to nu r bar c will have the same u1 charge. Okay, so this has a charge or lepton number 2. That means this term violates lepton number by 2 units. And if you can produce them in the colliders, you should be able to see same sign dilepton plus some dizet or some whatever you want. Okay, so this is a clear signature of lepton number violation. Only problem is that if if you have type 1 seesaw, this is going to be very difficult. So no future collider probably is going to reach the seesaw limit because this mixing suppressed. Even if you say that, okay, right-handed neutrinos are accessible in the collider, say TeV, but then this theta is going to be md by mr, which goes as the square root of the neutrino mass, which is 0.1 electron volt. Okay, but it's very small. Okay, so but if you have some other models like d minus L left-right model, you have extra interactions which can produce the right-handed neutrinos in the colliders efficiently without relying on the neutrino portals. But that is something like non-minimal. Okay, another interesting point about this model is that these right-handed neutrinos, they don't not only give you neutrino mass, they can also give you leptogenesis, which I will discuss in the third lecture. And you introduce three right-handed neutrinos, but 2 is enough because you only need to generate 2 masses. Okay, so you can always utilize the third one. You need not start with the third one. You can also always have a 2, but if you want to have, okay, I want to have a 3 because in the standard model I have 3 for everything, then the third one can be dark matter also. So it can solve neutrino mass, dark matter, leptogenesis, everything. Okay, and it can have some detection prospects also, as if you include dark matter, which I will talk about later on. I'm already running out of time. Another thing which we do not know in the neutrino physics is whether neutrinos are Dirac or Majorana. Now, in this model, type 1 seesaw, neutrinos are Majorana. Okay. Once you have lepton number violation, if it is going to mix with the light neutrino, that means light neutrinos are also Majorana. And you write down their masses. So if you draw the diagram, so this is N, R, and R. Okay, so this is, you can see the Newell and Newell are coming from both sides. So this is effectively writing like a term which looks like Majorana. Okay, and what we do not know is that whether neutrinos are Dirac or Majorana. The problem is that neutrino oscillations are not sensitive to this Dirac or Majorana phase. If neutrinos are Majorana, the one thing is that you cannot remove all the phases from the mixing matrix because of this term. If you write a term like this, if this term has a phase term, you cannot get rid of this, right? Because this is, as I say, this term has the same U1 charge as this one. So you will not be able to remove two of the phases from the mixing matrix. You remember there are 6 phases, 3 plus 6, 9, because it is a 3 cross 3 unitary. Out of 6, you can get rid of 5 if it is a Dirac. If it is Majorana, you can get rid of only 6 minus only 3. So 6 minus 5, so you can get rid of 6 minus 3. Okay, so then like 3. So 1 Dirac, 2 Majorana phases. But unfortunately, those Majorana phases are not going to affect neutrino oscillations, so you don't know them. So one clear signature is something called neutrinoless double beta decay, which will be, there's a lecture today, right? On this, there's a lecture today. So this is a clear signature. So what happens is that you have a down type quark and an up type. This is E, this is E. Okay. Yeah. So this you will see, which you otherwise don't see, because what you see in the 2 neutrino double beta decay, because neutrinos are Dirac, so it's like one neutrino is eating the other neutrino, because neutrinos are own antiparticles as far as the mass eigenstates are concerned. So you can think of that one Newell coming from this side and one Newell bar C going from this side. They meet because you write down the mass term as Newell C bar Newell, right? If it is Majorana. So you see that this is the lepton number violation. This is analogous to this process. Okay, if you see this process, you see this process also. But if you find out what is the contribution for this process to the double beta decay amplitude, this is basically, if you write, there's something called m beta beta, which is m beta beta is, I don't have time to talk about it. So this is basically u square, u alpha j square, m j, this term. And this, if I plot, I get something like this. I get something like this. So this guy is for M3 less than M1, and this region is for M3 more than M1, because both the possibilities are there. Now the thing is that if M beta beta, so the amplitude for this process is proportional to M beta beta. So if you see this process, it indicates neutrinos are Majorana. If you do not see this process, it does not say neutrinos are Dirac, because you can have a cancellation between different phases, because you have 2 extra phases now. So that will actually, that you can choose whatever you like, because there's no constraint from the experiments. So there's a reason which is in the normal ordering, which is where M3 is more than M1. It can be very, very small, far away from the experimental sensitivity. So not seeing neutrinos not seeing double beta decay does not tell anything about the Majorana or Dirac. But if you see, it's good. It clearly tells you that neutrinos have to be Majorana. And recently, people are working on this Dirac neutrinos also, because people had not seen Majorana neutrinos. So it's very interesting. We are also working on that. So Dirac neutrinos, they don't have this signature, but they can have other signatures, because you know that a Dirac fermion can be thought of as degenerate to Majorana fermions because of the degrees of freedom. Majorana fermion has 2 degrees of freedom, Dirac fermion has 4 degrees of freedom. So you are introducing extra degrees of freedom into your standard model, and all are light. Because when you say Dirac fermion is nu L, nu R, they are same mass, right? So you are adding 2 extra degrees of freedom, and if they are produced in the universe through some interactions, it will be seen in the, it will give rise to more radiation in the universe, which can affect all these CMB and and the structure formation. Okay, so that is actually tightly constrained by something called N effective. This effective relativistic degrees of freedom, and there are ways to calculate those things I wanted, but I don't have time. So if you're interested, I can discuss about these things later on. Okay, so sorry about yeah.
Thank you for your class. I would like you to explain better because I got a bit lost when you were talking about the solar neutrino problem, exactly in this upper centroid. Why were you in 2 dimensions? You forget about the M3 neutrino mass.
Yeah, you can extend it to 3 neutrino flavors also. You can do the same thing for the 3 flavors, but it will be complicated.
But you won't have the MSW effect.
We still have it. You'll still have, yeah,
I got it.
you'll still have it. MSW will still have it. But the thing is that if you add the third neutrino contribution is usually small because your theta 1,3 is very small. In fact, it was thought to be 0 initially, but now we know that this is around 9 degree. So it actually does not change much. Theta 1,2 is large, around 33, but this is 9. So it will contribute, but it's small.
Okay.
Yeah.
Further questions, Vita?
Thank you for the lecture. It was really good. I still have a issue with the another scalar, the heavy one that you introduced, the scalar one, the M one.
And
Yes, it's just a particle. It's a mass. Okay,
oh, this is a mass. It's a bare mass term. Yeah.
okay, but how this can solve the fine tuning issue?
Or it can solve the fine tuning issue because if you don't have this term, you need YD of the order of 10 to the power minus 10, because this term itself is going to give you the neutrino mass. If you have this term and you say that, okay, M is 10 to the power 14 or large, then you can have YD order 1. This mass will be sent at 10 to the power 2 GeV. MR is 10 to the 14. You get neutrino mass 0.1 electron volt. So there's no fine tuning.
Okay, great. And how all this stuff is compared with experiments? I mean, it fit well in the experiments or not?
I mean, as far as neutrino oscillation is concerned, all these models can give you the same neutrino data. So there's a huge degeneracy problem in that case. But if you are looking at the colliders or some other experiments where you are actually seeing these extra degrees of freedom directly, not indirectly, like neutrino masses, it can give you difference. For example, I mentioned that if you want to write this term directly without introducing right-handed neutrino, this is actually a triplet scalar field having 3 components, and it will have a doubly charged component, it will have a singly charged component, it will have a neutral component. And if you can produce them in the colliders, you will see again same sign dilepton, because delta plus plus will go to E plus E plus, which is there's no background in the standard model at all. You don't see that because in standard model lepton number is conserved. So, but if you want to look at type 1, as I mentioned, it is mixing suppressed. So it's very difficult unless you have some extra interaction which will produce the right-handed neutrinos.
Okay, good. Thank you.
So Debasish, could you remind them if we had just this Lagrangian standard model, just this one, and for some reason I could justify it by a discrete symmetry or gauge, whatever, but I don't care about the gauge symmetry. Can you fit neutrino oscillation data with just this term?
Can you say?
Can you fit neutrinos oscillation data with that?
Absolutely.
Yeah.
Absolutely. Because Y nu is a 3x3 matrix. I can put whatever I want.
So just to make sure, so the reason why so if we have just the Lagrangian, which is a Yukawa Lagrangian like in the standard model, we can explain neutrino data. Yeah, fine. But the standard model symmetry allows this term, which is what he emphasized. Well, if he allows, then we have to include it, right? So if it's not prohibited, so why you choose not to? So that's why he justifies everything he said.
Another question. Because of you diagonalize your Yukawa coupling, you get the oscillation for neutrinos. But should I expect oscillation on the right-handed neutrinos also? And what consequences would it have?
Oh yeah, that's a good question. You can think about right-handed neutrino oscillations also if they have very small mass splitting, because then only their wave functions will have a strong overlap. You can have it, but I mean, as you say, that can be interesting from, say, some kind of cosmology point of view.
Yes.
And it also depends upon the right-handed neutrino mass, what mass you are talking about. For example, if you have dark matter, one of the right-handed neutrinos is dark matter, you can produce right-handed neutrino dark matter from oscillations from active to sterile. You can do that. Okay, so that is called Dodelson withdrawal mechanism. Okay, so it is very interesting. And in leptogenesis also, there's something called resonant leptogenesis, where you have almost degenerate right-handed neutrinos. So if you are talking about very high temperature, very early universe, they can oscillate.
All right.
They can actually influence your lepton asymmetry also in resonant leptogenesis. So people talk about those things, but I mean, these are again, I mean, you will not be able to say directly. I mean, like we probe neutrino oscillation directly, because these are model dependent statements. Right-handed neutrinos are there, and what mass, and yeah. But in principle, it's possible.
Nice. Thanks.
Do you have one more question? No. So for those who are in the audience, you can leave your questions there. We're gonna address them tomorrow. Okay. So the Debasish is here upstairs on the second floor. You can just meet him and bug him anytime.
Yeah.
So thank you so much. I see you all tomorrow.